So I was showing pictures of graphs, and I was saying that the inverse function has a graph which is the same as the graph of the original function, but flipped. Let me be more specific. The graph of the inverse function is mirrored across the line y equals x. So let's go ahead and see this in the graph. So here is the graph of the function e to the x in blue. And to graph its derivative, I'm just going to write, instead of y equals f of x, I'm going to write x equals f of y. And there it is in green. And if you don't believe me that that is the inverse, I'll turn that off and let's graph instead y equals the natural logarithm of x. The very same thing. Notice that these two graphs are mirrored across this 45-degree line running through the origin. So, what does that mean? In calculus, we like to understand functions by studying their derivatives, right? The slope of the tangent line at any given point will tell us useful information for working with functions and for understanding functions better than we did before. So these two curves have some sort of geometrical relationship to each other, right? If I knew the slope of the blue curve, can't I just reflect that across and get some information about the slope of the red curve? Oh, yes, let's give this a try. Let's give this a try right now. So let's say that I have a function, call it f of x, and I have its inverse function. I'll call that f inverse. So here my superscript of the -1 tells me this is the inverse function. How would I go about differentiating f inverse? Maybe f inverse is harder to differentiate than my original function f. Well, I'm going to use this same trick again. This is the very same way that I calculated the derivative of the natural logarithm function way back when. The graph of y equals f inverse of x is the very same graph as x equals f of y. So the graphs of both of these equations are telling me that the coordinate x comma y satisfies the rule y is equal to f inverse of x. Or equivalently, x is equal to f of y. So these two different graphs will give me the very same function, just like I showed with my logarithm graph a few minutes ago. Now, maybe my original f of x is easier to differentiate, so I'll use implicit differentiation. I can take the implicit derivative of any equation, just as long as I'm careful about my dy on dx's. So if x is equal to f of y, then it must be the case that the derivative of x is equal to the derivative of f of y. On the left-hand side, that'll be equal to 1. And on the right-hand side, that will be equal to f prime of y times y prime. So I'm using the Lagrange notation for that. Well, the thing I want is y prime, so I'm going to rearrange my equation. Y prime must be 1 divided by f prime of y. That's a little funny. Usually I like my y primes to be equal to some function of x, but I can fix that if I remember that this y down here is also equal to this f inverse of x on the very first line I wrote in this calculation. So for any inverse function, y prime, or f prime of x if you prefer, is equal to 1 divided by the derivative of f evaluated at f inverse of x. I'll say it again a slightly different way. The derivative of an inverse function is 1 divided by the derivative of the original function whose input is the inverse function. Another way to think about that. So we will be using this to learn derivatives for a more complicated set of functions, the inverse trig functions.